Ever wondered why your coffee stays hot longer in a thermos? Or why your mirror seems to reverse left and right but not up and down? Welcome to the world of everyday physics, the unseen forces that shape our daily lives. Physics isn't just about black holes and quantum mechanics, it's about understanding the world around us. And that world is full of fascinating phenomena, from the way heat is transferred, keeping your coffee hot in a thermos, to the way light behaves, causing your mirror to flip your image. Every moment of our day, from the moment we wake up to the sound of an alarm, to when we switch off our lights at night, physics is at play. It's in the music we listen to, the sports we play, even in the electronics we use. So let's embark on this journey of discovery together. Stay tuned as we dive deeper into the fascinating physics phenomena that are at play in our daily lives. Your morning coffee ritual involves more than just a caffeine fix. It's a lesson in physics. Yes, you heard that right, physics. The humble thermos flask is a silent witness to this everyday marvel of heat transfer and insulation. Let's take a closer look. When you pour hot coffee into the flask, the heat energy from the coffee tries to escape. This is where the principles of conduction, convection, and radiation come into play. Conduction is the transfer of heat through direct contact. The heat from the coffee spreads to the inner wall of the flask. But here's the catch. The thermos is designed to minimize conduction. The inner and outer walls are separated by a vacuum, which is a poor conductor of heat. So the heat from the inner wall doesn't easily pass to the outer wall. Then there's convection, the transfer of heat through fluids. The hot coffee molecules move around, causing a heat current. But again, the thermos outsmarts convection. The narrow neck of the flask restricts the movement of the hot air, reducing heat loss through convection. Lastly, we have radiation, the transfer of heat in the form of electromagnetic waves. These waves can travel through a vacuum, so the vacuum in the thermos can't stop them. But the thermos has another trick up its sleeve. The inner wall is coated with a reflective layer that bounces back the radiant heat towards the coffee, preventing heat loss. Together, these three heat transfer methods, conduction, convection, and radiation, explain how your thermos keeps your coffee hot for hours. It's a wonderful example of how physics is at work in our everyday life. Physics is not just about complex equations and giant particle accelerators. It's also in the simple things, like enjoying a warm cup of coffee. So the next time you sip your hot coffee from a thermos, remember the complex physics at play that keeps it warm. Mirrors do more than just reflect your image. They're a fascinating study in physics. When light, traveling as waves, hits a smooth surface like a mirror, it bounces back. This phenomenon is known as reflection. The angle at which the light hits the mirror, the angle of incidence, equals the angle at which it reflects, the angle of reflection. This is a fundamental law of light physics, and it's what enables mirrors to give us a pretty accurate reflection of ourselves and the world around us. Now, let's delve a little deeper. Mirrors that we commonly use, like the one in your bathroom or the rear-view mirror in your car, are called plane mirrors. They have a flat, reflective surface, and they produce what we call a virtual image. A virtual image is an image that appears to be at the location of the light source but isn't actually there. It's like when you look into a mirror and see your face. Your face isn't actually inside the mirror, right? It's just an image formed by reflected light rays that seem to be coming from a point behind the mirror. And here's a fun fact. The image you see in a plane mirror is always the same size as the object and located the same distance from the mirror as the object. It's just flipped laterally, which is why your left appears on the right, and vice versa. Also, because light travels in straight lines, plane mirrors can only reflect light that hits them. That's why you can't see around corners with a mirror unless you angle it just right to catch the light bouncing off the object you want to see. So the next time you look into a mirror, remember that it's not magic but physics that makes your reflection appear. Music is more than just a melody, it's a symphony of physics. Let's delve into the world of sound waves and how they create the music we love and enjoy. Sound waves, like ocean waves, roll through the air, but in a much faster and less visible manner. They're created by things vibrating. The strings on a violin, the diaphragm of a speaker, the vocal cords in your throat. These vibrations push and pull on the surrounding air molecules, causing them to bunch together and then spread apart. This pattern of compression and rarefaction moves outwards, creating a wave of sound. Now, what gives this sound wave a specific note? That's down to its frequency, or how many waves pass a point in a given amount of time. A high-frequency sound wave, with lots of waves close together, will sound high-pitched, like the squeak of a mouse. On the other hand, A low-frequency sound wave with waves further apart will sound low-pitched, like the roar of a lion. The loudness of the sound, on the other hand, is determined by the amplitude of the wave, or how far the air particles are pushed and pulled. The bigger the push and pull, the louder the sound. But we're not done yet. The physics of sound also includes a fascinating concept called resonance. This is when an object vibrates at a particular frequency. It can make other objects vibrate at that same frequency. This is why a singer can shatter a glass with her voice, or why a particular note on a piano can make a wine glass hum. The frequency of the sound matches the natural frequency of the glass, causing it to vibrate too. So, when you strum a guitar, blow a trumpet, or simply clap your hands, you're not just making noise, you're creating a complex pattern of vibrations in the air, a symphony of physics that our brains interpret as music. So, when you listen to your favorite song, remember that it's physics that makes it possible. Playing sports involves more than just skill. It's a game of physics. Indeed, the essence of physics is deeply intertwined with the athletic world. It's all about motion, force, and the play between inertia and acceleration. Let's break these down. Motion in physics describes the movement of an object. It's the change in position of the body with respect to its surroundings in a given period of time. In sports, this is translated into the movement of players, the ball, or even equipment. Think about a basketball player shooting a free throw. The player uses motion to propel the ball towards the hoop. Force, on the other hand, is the push or pull that causes the ball to move. It's the player's hand applying pressure to the ball, causing it to move in a specific direction. Force is also the reason why a soccer ball curves when a player kicks it with a spin. The force applied by the foot on different parts of the ball causes it to follow a curved path. Now let's look at inertia and acceleration. Inertia is the tendency of an object to resist changes in its state of motion. A baseball, for instance, will continue to stay at rest until the pitcher applies a force to it. Similarly, a sprinter at the starting line will remain at rest until a force, in this case the sprinter's leg muscles, propels them forward. Acceleration, on the other hand, is the rate at which an object changes its velocity. A cyclist, for example, starts slow and gradually picks up speed. This change in speed over time is acceleration. In a nutshell, the physics of motion is a central player in the world of sports. It dictates how athletes move, how balls are thrown, kicked, or hit, and how races are won or lost. It's a complex interplay of laws and principles that add depth and dimension to the games we love. So the next time you play or watch a sport, remember that physics is the real MVP. Using electronics involves more than just pressing buttons. It's a circuit of physics. Let's delve into the fascinating world of electricity and electronics, and how physics powers them. Electricity is the lifeblood of our modern world, powering everything from the humble light bulb to the sophisticated computer systems. But what is electricity? Simply put, electricity is the movement of electrons, tiny particles that carry a negative charge. This movement of electrons creates an electric current. Now let's talk about the three fundamental building blocks of electricity: voltage, current, and resistance. Imagine electricity as water flowing through a pipe. Voltage, also known as electric potential difference, is akin to the water pressure. It's the force that pushes the electrons through a circuit. The higher the voltage, the more force there is to move the electrons, creating a stronger electric current. Speaking of which, current is the rate at which the electrons flow through the circuit. It's like the amount of water flowing through the pipe per second. The larger the current, the more electrons are moving, and the more electricity is being transferred. Lastly, resistance is what hinders the flow of electrons. It's like the roughness of the pipe's interior that slows down the water flow. In an electric circuit, resistance is caused by the material of the wire and its temperature, among other things. The higher the resistance, the less current can flow for a given voltage. These three elements interact in every electronic device we use. For instance, in a light bulb, the filament provides resistance, the battery or power source provides the voltage, and the current is the flow of electrons that lights up the bulb. So the next time you use an electronic device, remember that it's physics that powers it. It's not just about pressing buttons, but about a complex interplay of voltage, current, and resistance. And that, my friends, is the beauty of the physics of electricity and electronics. Physics isn't just a subject in school, it's a part of our daily lives. Indeed, this journey we've embarked on has unraveled the magic that is physics, hidden in plain sight within the mundanity of our everyday lives. From the moment we wake up to the time we retire at night, Physics is our silent companion, shaping and guiding our experiences. We started our exploration with the physics of heat. The humble thermos flask, a staple in many households, utilizes the principles of conduction, convection, and radiation to maintain the temperature of your drinks. It's a simple yet fascinating illustration of how physics impacts our daily routines. Next, we delved into the realm of light, focusing on how mirrors manipulate it. Mirrors, whether in our bathrooms or in our vehicles, create reflections through the laws of light physics. They bounce light in ways that provide us with images, enhancing our perception of the world. Our journey then took us to the world of sound and music. We discovered how physics is instrumental in creating the beautiful symphony of sounds we enjoy. From the strum of a guitar to the beat of a drum, physics is the invisible conductor orchestrating this melodic harmony. We also ventured into the exhilarating domain of motion and sports. Whether it's a ball soaring across a football field or a gymnast gracefully defying gravity, physics is at play. It's the invisible playbook that athletes intuitively follow, shaping the rhythm and rules of every game. Finally, we explored the vast landscape of electricity and electronics. The devices we rely on, from our smartphones to our refrigerators, owe their functionality to the principles of electrical physics. They are tangible manifestations of how physics powers our modern world. As we wrap up this journey, let's remember that the magic of physics doesn't end here. It's ever present, unfolding around us in every moment. It's in the boiling kettle, the setting sun, the singing bird, and the falling leaf. Remember, every day is a physics lab, and you are the scientist. Keep observing and keep learning.